Good afternoon. Welcome to the last session of the third day of the conference. This session is named Professor Lalit Mohan Nath Memorial Session, and the session chair will be Professor Ashoke Sen of International Center for Theoretical Science, ISTS, Bangalore, India. I'm inviting Professor Ashoke Sen to start the session.
Okay, so welcome to session 10 of this conference. So this session is the Professor Lalit Mohan Nath Memorial Session. Lalit Mohan Nath was a Bangladeshi nuclear physicist. He was a professor in the Department of Physics at the University of Dhaka. Nath obtained his BSc Honours degree in Physics, standing first in the first class in order of merit, and his MSc degree in Physics, standing second in the first class in order of merit. He then went to University of Edinburgh to undertake work on electromagnetic interactions of charged particles in the quantum theory of fields of spin 1 and 2 particles under the supervision of Nicholas Kramer and Peter W. Higgs, and obtaining his PhD degree in theoretical physics in 1964. Nath joined the University of Dhaka, Bangladesh in September 1972 and served until June 2001. He became Professor of Physics in 1981 and became the chairman of the Department of Physics from July 1994 until June 1996. Nath was a visiting scholar at the University of Western Ontario, Canada during December 1971 to June 1972, at the Florida State University during August 1969 to November 1971, and at the Purdue University during September 1967 to August 1969. Nath was an associate of the Abdus Salam International Center for Theoretical Physics, Italy, from January until August 1967. He also worked for some time in the Bangladesh Atomic Energy Commission as a senior scientific officer from December 1964 to December 1966. Okay. So with this, we'll now start the session. So the first speaker is Mahmoud Ul Hassan. He will talk about integrable system from water to Bose-Einstein condensate.
Thank you. Thank you very much. Good afternoon, everybody. First of all, I would like to thank Kamrul Hassan Sahab and Supriya Saha Sahiba for their kind invitation for this conference. So in this talk, I'm going to give an introduction, a kind of introduction to integrable systems and its relation to Bose-Einstein condensates. So, so basically, we will I will talk about a generalization of a non-linear Schrodinger equation, which is a kind of non-abelian generalization based on some Lie group, and from that generalized equation, we shall derive three-component Gauss-Petrowski equation, which describes the dynamics of Bose-Einstein condensate. So after that, I will talk about a relativistically invariant field theory, which is also integrable, and we'll find out the solutions, exact solutions of that equation. So let us move to the next slide. So when I was an undergraduate student at Government College Lahore, I wanted to be an experimental particle physicist But soon I realized that it's going to be very expensive for Pakistan to establish these things. So I moved my attention to mathematics, and still I came to believe in Vladimir Arnold's statement that mathematics is an experimental science, as we know that Jacobi identity is in fact an experimental fact. So we make experiments, we can make experiments in mathematics. So this talk is all about mathematics related to experiments. So now the question is, why do we need integrability? Integrability is an important property of differential equations because not only it invokes the word integration, so the integration of differential equations, but not only the differential systems, we can have integration of different systems, discrete and semi-discrete systems. So the solving these mechanical and astronomical problems, so this history goes back to Kepler, Galileo, Newton, and they try to find out the exact solutions of mechanical problems. So most of the physical problems are non-solvable by the analytical methods available in mathematics, but there are quite few systems which are integrable in the sense that we can find the exact solutions. So these systems lie in these broader classes of classical mechanics, quantum mechanics, statistical mechanics, and quantum field theory. And the other aspect of integrable systems is that they provide non-perturbative aspects. So we can, in fact, compute exact results, and even in quantum field theory. And they also, the beautiful thing is that they also provide an interface of mathematics and physics. So if we go back to the history, so we know that Kepler's two-body problem is completely solvable, and it was solved by Newton, and solved by quadrature, which means that we reduce all the equations of motion to finite steps of integrations. So then in 1887, Poincaré showed that a general analytical solution for a Newtonian planar three-body problem does not exist. So the motion of three bodies is generally non-integrable except in special cases. But when we increase the degrees of freedom, then there is the possibility of having integrability, maintaining the integrability of the system. So this revival came back in the observation by John Scott Russell in 1837. So he observed the wave of translation, now called soliton, in the Glasgow-Edinburgh Canal. And the mathematical theory of this wave of translation was developed by Korteweg and De Vries, and now this is known as the KdV equation, which is a nonlinear equation of water waves, shallow water waves. So KdV is also an example of an infinite dimensional Hamiltonian system, which is a prototype example of integrable systems. So this is the KdV equation, where U is a function of x and t, and the subscript represents the derivative. So after almost 70 years, in 1960s, this method, a wonderful method was developed, inverse scattering method was developed by these persons, Gardner, Graine, Kruskal, and Moire, and they found this solution, analytical solution of the KdV equation, which represents the soliton. So soliton, so these are the solitons in water waves. So two solitons are interacting in such a way that this is like kind of collision of two particles. So we can have multi-soliton configurations where they collide with each other and they maintain their shape after the collision. So this picture was taken by Mark Ablowitz. And these are the pictures. First picture is a one soliton, and the second is two solitons interacting with each other, and these are the three solitons interacting with each other. So these are from some of my papers. So now we define the integrable systems. So we start with a manifold which is called the phase space. And the phase space is a smooth manifold and is two-n-dimensional and is generated by these two quantities qi and pi, position and momenta. And on this manifold, we define a smooth function f. F is a smooth function from this product manifold to the real line, and this function is called the dynamical variable. And the two dynamical variables f and g obey this Poisson bracket. So if we have two dynamical variables f and g on the phase space, then if the Poisson bracket is 0, then we say that f and g are in involution. And we have special dynamical variable, which is the total energy of the system, and is called the Hamiltonian, which is also a function on the phase space. Now the Hamiltonian determines the evolution of the system. So we can see it here. So if we find out the rate of change of time evolution of a variable, dynamical variable in the phase space, so this is given by this simple equation. And if f does not depend explicitly on time, then it is f dot is just equal to the Poisson bracket of f with h. So which means h is the determining factor of the flow. So the flow is determined by the total energy. So the conserved, if this bracket is 0, f with h is 0, then f dot is 0. So that is the constant of motion. So we get conserved quantity. So now we explain the Liouville integrability, notion of Liouville integrability. So a Hamiltonian system represented by a Hamiltonian on the phase space M is said to be completely integrable if there exists a maximal set of n algebraically independent non-trivial local constants of motion in involution. So the second condition is that they should be in involution, which means that they are independent with each other, which means that they are linearly independent and they Poisson commute with each other. So this is a very important property in explaining integrability. And then Arnold extended this theorem further, and this theorem states that for a Liouville integrable system on the phase space, there exists a canonical transformation. So we make a canonical transformation on the phase space to some action angle variables, j and phi, in which the system is completely separable. In that sense, we get a Hamilton-Jacobi equation, which is completely separable, and then we get all the momenta become constants. So the canonical equations, Hamilton's equations, reduce to these two equations. J dot is 0 and phi dot is the frequency. Now the actions are functions of integrals of motion. So all the actions are functions of all the conserved quantities. So they are constant in time, and only the angle variable determines the flow. So the variable evolves linearly because this is simple linear equation. So this evolves linearly in terms of these frequencies. So we can determine the frequency, and then we say that the solutions of equations of motion are obtained by quadrature. So quadrature means that we have to perform finite steps and algebraic operations and integrations in terms of some known functions like trig functions and hyperbolic functions, etc. So the existence of n Poisson commuting independent invariants implies that the trajectory of the system, now this is the constraint. So these conserved quantities constrain the system to move on an n-dimensional manifold MF, so which is the submanifold of the phase space. So this manifold is determined by F. So we write it as MF, and this is the level. So this is kind of level surface on the manifold and is determined by the integrals of motion and is embedded in the bigger manifold, which is the phase space, 2n dimensional. So MF is determined by all these CIs, where CIs are the constants. So the validity, so now the conservation law implies that the trajectories will always remain on this level surface. So they will never leave the level surface. So this is another result of differential geometry, that this manifold has the topology of an n-dimensional torus, which means that this is the product of n circles. And this is the theorem, and the theorem is that a compact manifold of dimension n, which admits n commuting vector fields, is diffeomorphic to an n torus. So which means that all the manifolds, submanifolds, which are determined by the constants of motion are they are in fact the tori, different tori determined at for different conserved quantities. So this forces the phase space to admit a foliation. So the phase space is foliated into an in n-dimensional leaf. So each leaf is a submanifold and is determined by the constant of motion. So each leaf is a torus, and tori correspond to different choices of these constants C1, C2, and Cn. So we can say that the Hamiltonian system is, integrability of the Hamiltonian system is equivalent to the foliation of the phase space by invariant tori. And these tori are also known as Liouville tori. So the leaves of the foliations are embedded in the manifold, and they are invariant under the flow. So one dimension, for example, example of integrability is the simple harmonic oscillator is an integrable system. So the phase space is foliated by concentric ellipses, which are one-dimensional tori. So this is the foliation. So every leaf, so every torus has an inner torus and an inner torus, and the trajectories on each torus. So this is the geometry of an integrable system. And in summary, so we have systems, dynamical systems on the phase space, and for integrable systems, there exist maximal Poisson commuting set of quantities, Fi, and the motion is confined to a leaf of the foliation at Fi is equal to Ci, and there exists a canonical transformation that makes the system evolve linearly on the leaf, which means that we can find the frequency of motion, and the system is solvable by quadrature. So this is all about review of integrability. So one aspect of integrable system is that we can represent them. The nonlinear problem is represented in terms of a linear problem, which is in fact an eigenvalue problem. So once we know the eigenvalues and the eigenfunctions, we can find the solution of the nonlinear problem. So these are, Lax pair is a set of two operators L and M, and they obey this Lax equation. And if we have this Lax representation, we can directly find out the conserved quantities by taking power of L, trace of power of L. So we can generate a lot of conserved quantities. So now we move on to field theories. So for field theories, we know that field theories are infinite dimensional Hamiltonian systems, and so they will require infinite number of conserved quantities in involution for them to be integrable. So in this case, when we have a continuous system, a continuum, these solutions are known as solitons. So KDV is an example of an infinite dimensional system. So KDV has infinite number of conserved quantities. So the solutions are solitons. And solitons have three basic properties. They are localized, they keep their localized form over time, and this form is preserved under the interaction with other solitons. So once we have an integrable system, we can solve it by inverse scattering transform. And there are other methods of finding these solutions. So these systems are not only classical scalar systems, but we can have systems which are non-abelian, taking values where functions take values on some Lie groups or Lie algebras or some symmetric spaces. And we can have the non-commutative systems. Quantum systems are also non-commutative because they involve operators, non-commuting operators. And supersymmetry is a kind of non-commutativity. So what we use in this case, we express these solutions in the term of determinants. So these are special kind of determinants introduced by Guelph and Retach and back in 1991. So these are we are familiar with the determinants which are determinants of matrices with commuting entries. But here we are dealing with non-commuting entries, which means that every entry is itself is a matrix or some operator or some other kind of non-commuting object. So if we have n by n matrix over a ring R, which is generally non-commutative, then we'll have n square determinants. So if we look at the case of when X is a two-dimensional 2 by 2 matrix, then we have 4 quasi determinants. And in the commutative limit, when we assume that all the quantities commute with each other, then this determinant becomes a ratio of 2 determinants, so ordinary determinants. So we express our solutions in terms of these determinants, so that's why we are introducing it here. So other property of quasi determinants is they obey this non-commutative Jacobi identity. So this Jacobi identity also reduces to the commutative Jacobi identity under the commutative law. So here we can relate different sized, these are some properties of, and they also obey these homological relations. So different determinants are related with each other. Now we take an example of a non-abelian NLS, which is non-linear Schrodinger equation, and a relativistically invariant field theory with chiral symmetry, which is in fact a model of strongly interacting gauge field theory in 4 dimensions. So they have all the properties of gauge theories. So the non-abelian nonlinear Schrodinger equation has a relation with Bose-Einstein condensate, but when we make a reduction, so we start with a this set of Lax operators L and M, where U and T are matrices. U matrix involves some kind of functions of space and time, and they are bigger sized matrices, P plus Q sized. Sorry? 5 plus 5? 5 minutes. Okay. Okay. So with this Lax pair, we end up with this is the condition, compatibility condition of the Lax pair. So this is equivalent to an equation. So this is the equation, which is a non-abelian Schrodinger equation, non-linear equation. And for the matrix, if we put this matrix U, and these are the other matrix which reside inside the matrix, then we are left with this equation. So we use this equation, we apply a transformation which is known as Darboux transformation. So this is algebraic method of finding a solution of this kind, of this equation. So the solution is written in terms of this equation. So this is the solution U, which is written in the form of a Cauchy determinant, where everything in it, theta 1, theta 2, theta 3, lambda 1, they are the matrix solutions to a linear problem. So a nonlinear problem is reduced to a linear problem. So if we put the functions in these matrices in this solution, we end up with different solitons. So this is the Cauchy determinant solution of the nonlinear, non-abelian nonlinear Schrödinger equation. And when we take this U2 to be this equation, we end up with 3 component coupled equation, nonlinear Schrödinger equations. And these are called the 3 component Gross-Pitowski equations. And the solutions can be written, so let me explain this. So these 3 equations, in fact, we know that if an atom possesses a spin F, the spinor Bose-Einstein condensate is described by 2F plus 1 component wave function. So we end up with 2F plus 1 coupled equations. So in this way, different spinor Bose-Einstein condensates can be embedded in the framework of integrable systems. So under specific approximations like mean field approximation, we get integrable equation. Otherwise, in general, they are non-integrable. So the solutions which we find through this Darboux transformation are these solutions, the 1 soliton and 2 solitons. So this is only U1. So now I move on to the relativistically invariant equation. So this is called harmonic maps into Lie groups. So phi is a map from the manifold M to N. So they are two Riemannian or Lorentzian manifolds. And then we define the density as a functional of the density of the map, where E is the density of the map, which is also a smooth function from M to R, is a real function. And density is given by this differential, and this differential maps, df maps the tangent space in M to a tangent space in N. And in terms of local coordinates, we write it density in this form, which is nothing but the equation of motion of a nonlinear sigma model, and it's all a Lagrange equation. So we are familiar with ordinary harmonic function, which is a harmonic map from Rn to R. And if the map is from R to M, so manifold, then this is a geodesic. And similarly, so the map which has a chiral symmetry is a map from R11, which is 2-dimensional Lorentzian manifold, to some Lie group. Lie group is also a manifold in this case. So this is the map into the Lie group, and this is the action. And from the action, we get the equation of motion, which is a pure gauge. The equation of motion gives us another condition. And this is the conservation law, which directly follows from the Lagrangian. So we have so equation of motion itself is a conservation law. And in the light cone coordinates, this is written in this way. And we can expand it in terms of generators of the Lie algebra. So the Lie algebra obeys these commutation relations. And so the action is invariant under this chiral symmetry. So we have left current and the right current. And in terms of these currents, we can find out the solutions. And this is another property. The currents obey the conservation law and also obey this extra condition, which is called the zero curvature condition. Now from this we can compute an infinite set of local quantities. Since all the currents are algebra valued, so this K, so every current is associated with invariant symmetric tensors of the underlying Lie algebra. And the spins of these conserved quantities are equal to the exponents of modulo the Coxeter number of the classical Lie algebra. So they have a good explanation in the language of Lie algebra. So these are all in commuting with each other. So this is the Lex pair of the chiral field. And from the Lex pair, again, we find the solution in terms of causative determinants, in terms of the linear problem. So all these matrices M1, M2 are linear. And from the linear solution, we get the harmonics. So these are the multi-harmonic maps. And these are also solitons. So for the first case, when we have single one solution harmonic map, which is a combination of a kink, and so this part is a sine hyperbolic part is a kink, and secant hyperbolic is a soliton. So we end up with these solutions. These are the solutions which we find out by applying algebraic method on the differential equations. So these are a few results that I would like to share with you. Thank you very much. You have to push the button.
You showed solitons of the KdV equation
Yes.
interacting with each other, keeping their form. Do they also form Lax pairs?
Yes, KdV has a Lex pair.
Hmm.
Almost every integrable system has a Lex pair. If it is solvable by the inverse scattering method, so there will be a Lex pair.
So how do you identify those matrices? So d by dt of something is equal to commutator equals 0. How do you identify those matrices?
Lax matrices are not easy to find. So there is if we solve a system by inverse scattering method, we get a clue that we can form a Lax pair. So this is not an easy problem to find a Lax pair. So it takes a lot of work. So, but in the inverse scattering method, we get a way to find a Lax pair.
Mm.
Yeah, sure.
Hello, wonderful talk. I just wanted to ask whether you consider the zero curvature condition for the nonlinear Schrodinger equation, because maybe I somehow skipped it in your presentation. Or
You want to see the zero curvature condition
Yeah.
in the case of, so which is just the commutator is just equal to 0, L and M. So in this case, you see I've written the derivative inside this operator. So so if L and M, so these are not, don't confuse it with the previous L and M, because in the previous case, so you see these, so this is for simple classical system where we have Lax operators in this form, and the equation is written in an eigenvalue problem. So this is also a representation, and if we write the Lax pair with both space and time derivatives in this way, then the zero curvature condition is just equal to this.
so the compatibility condition is the zero curvature
Yes.
condition. Okay. Thank you.
Professor Mahmoodul Hassan, maybe I have not followed anything. That's why some questions are there. You have talked about the integrable system, yeah?
Sorry.
From water to
Where is the?
Bose-Einstein condensate.
Yes, sure. Yeah. So what is the question?
Question is, I didn't. You have been working on that, but I have not. You have not touched anything on Cauchy-Riemann conditions or the integral.
Cauchy-Riemann
Yeah. Conditions for
complex analysis. Cauchy-Riemann. I think Cauchy-Riemann equation is equivalent to this.
conditions for analytical functions.
No,
for
I think we don't need that.
You don't need
this. Yes. So we only need the compatibility conditions of operators, Lax operators.
Did you ever utter anything from water to Bose-Einstein
Yes,
condensate?
because we observed this phenomena, integrability in water waves. So KDV is an example of shallow water waves. So it is observed in, and also in Bose-Einstein condensate in the form of Gauss-Petosky equation, and even in quantum field theory in the form of chiral models.
Okay, thank you.
Hello.
Any other?
I have a question. You have written a Schrodinger equation which is non-linear. Is there any physical system other than Bose-Einstein condensate where we can use this non-linear Schrodinger equation?
Yes, there are many fiber optics and other optical transmission lines. So they are represented by nonlinear Schrodinger. Even in biological materials, this equation appears, and we have the solitron solutions.
Thank you.
End this talk here, and let's thank the speaker once more. Okay. The next speaker is Rajdeep Sen Sharma, and I don't know your title, but it will appear soon, I guess. Okay. Strong correlations in Moire materials. So I'll tell you after 20 minutes.
Let me first thank all the organizers of this very wonderful conference for inviting me here and giving me this opportunity to speak here. This is my second visit to Dhaka, the first one when I was very young in school, which I kind of vaguely remember, but I'm sure I will remember this visit much more vividly. One thing about, unlike other senior people, we have had no direct connection to Professor S.N. Bose. He was our hero, of course, I mean, and probably played a role in going to the college which he shared, which was Presidency College. But he had always been the person whom we had learned in our textbooks. So with that, I'll tell you today about strong correlations in a new class of materials that people have been manufacturing, building, and which has shown some very, very interesting phenomenology over the last maybe 5 years, 6 years. So before I get on to the actual topic of my talk, let me just point out that, which has been pointed out by many people, that quantum particles, even if you take two, you have to have additional ideas of indistinguishability. And suddenly they come in two kinds. One was bosons, where two indistinguishable particles can share the same quantum state. For example, they're happy children. They can share their toys and so on and so forth. And this was led Bose to his famous counting, and then led to the Bose-Einstein distribution. On the other hand, there are fermions, which are where two indistinguishable particles cannot share the same quantum state. This is called Pauli exclusion principle. They're like children who are always fighting about their toys. They can't share anything. And this leads to a large class of phenomena on their own. Almost all of electronic structure, the fact that we have so many different kinds of atoms, all sorts of chemistry, condensed matter, and various things are essentially have at its heart the fact that there are fermions and there's Pauli exclusion principle. what I will hopefully, my talk will mostly veer on the direction of fermions, but hopefully towards the end you will see bosons appearing in some of this. So let's first talk a little bit about Moire patterns. These are patterns which are created by interference from regular structures. So if you look at this, you will see that I have two bunch of concentric rings. I've superposed them on one another. And what I'm going to do is I'm going to make the center go back and forth like this. And suddenly you will see that there are all sorts of radial patterns emerging, periodic structures. And the length scale of these radial patterns, if you look at where their intercepts are and so on, they don't usually have something to do with the periodicity of the rings that we had started with. Okay? So the idea that I can take two very regular patterns and then slightly shift them or slightly rotate them and create patterns where the length almost periodic patterns, where the length scales are much more different from the microscopic patterns, microscopic length scales, periodicities. This is basically known as Moire patterns. Okay, you can look at it a little bit on the other one. I hope I can get it going. Yeah, these are basically just two sets of lines, and this is where they could be superposed on each other, and all they're doing is they're rotating them, the axis of these lines with respect to each other. You can see these interference patterns forming, and you can also see how they're becoming large and small, well separated, and so on. So the other thing that you realize is that these patterns are extremely sensitive to the small shifts and rotations you are going to put. So you take two patterns, two regular patterns, shift them a little bit, and suddenly you get a length scale or a new pattern which is very different from this. And the last one is basically, again, this is radial things where things are just rotating with respect to each other. And you see that the pattern that you can visually see you wouldn't have predicted it if I just told you these were radial things which are just rotating with respect to each other. So why are we talking about Moire patterns? Well, one of the things is that Moire patterns are ubiquitous in nature. The name itself comes from certain kinds of Moire fabric or certain kinds of watered silk, which hopefully you can see here. You can see these textures on the textile, and these are patterns created by two different weaves of the silk that's happening here. If you are going on a television, people would tell you, don't wear striped shirts, okay? Because they don't look too good. This is what happens when you take photos or television cameras with a striped shirt. What happens is that the camera has some pixelization and your stripes have some periodicity, and slight misalignment will give rise to this Moire pattern that you are basically seeing on there. Okay? These have been used in very important ways. They're used to create marine navigation lights. I told you that these patterns are very sensitive to exactly how much shift or rotation you have done. So what people do is they put these patterns on currency notes. Okay? So if I'm trying to forge a currency note, it's very hard for me to get the shifter thing exactly right, which means the Moire pattern that is on the currency note will be very hard to reproduce. And this is how, for example, a lot of currency note frauds are checked and so on. These are also used in physics for strain measurements in materials, but let's not go into this. So the point is that you will see this kind of patterns all over the place in various forms in nature all around you. Now, I'm a condensed matter physicist, so why am I talking about textured silk and currency notes? And so if you think for a while, you will see that the main point is that you had two periodic patterns and there was interference between them. And then you shifted one of them and you got these new interference patterns. That's what is happening at the base of this. Now, if you go back to a solid, what happens is, this is a cartoon picture of a solid. You have these ions, which are essentially forming a periodic lattice. and you have a fluid of electrons which are moving in the background of this periodic potential created by the ions or lattice. Okay? And the scattering of these electron waves by the periodic potential of the lattice is what gives rise to bands. So if you look at, for example, a momentum energy dispersion relation, you will see that your nice k square over 2m will now, due to this fact that you are getting scattered by the periodic potential, you will create all these parts where you can have traveling waves, and then parts where you cannot have traveling waves, and those are the band gaps and the bands and the band gaps and so on and so forth. And now you can see where I'm headed. If interference is giving rise to this, all the electronic band structures and from a periodic potential, what if I can create a Moire periodic potential? Okay? Maybe I will get some very interesting band structures coming out of this. Maybe I'll get something more interesting. So what do I need from this? So interference of electron waves from periodic lattices bands, interference from regular patterns which are slightly rotated, shifted, are Moire patterns, and these are large-scale patterns sensitive to rotations. So if you can create Moire patterns out of lattices, the band structure should be sensitive to your twists and so on. And anytime you can tell condensed matter experimentalists that they have a new tool to control electronic properties of materials, it always leads to something interesting and so on and so forth. Okay? So the idea was that you take these 2D materials, van der Waals materials, you place one on top of another, okay? They have their crystal axis, and you rotate the crystal axis a little bit, okay? And it's almost amazing that nowadays experimentalists can do this with a precision of 0.1 degree. They can basically make two lattices lie on top of each other and rotate them with an accuracy of about 0.1 degree. Now, you need electron waves from these two layers to interfere because you need the two patterns to interfere. And that's why you need to place them close by, because you need tunneling between the layers, and that would lead to these Moire materials. Now, what kind of 2D materials you can have? The one that is most famous, most used, is graphene. Graphene is basically a sheet of carbon atoms arranged in honeycomb lattice. Let's not get into all the details of sublattice and pseudospin. What happens is that the band structure is plotted there, and you can see that there are these 6 points where the red and the blue band touch each other, and these are called Dirac points. If you expand around those momenta, you will see that the low energy dispersion is linear, like a Dirac dispersion. Okay? And then there are two inequivalent points, so there are 2 degrees of freedom, 2 valleys, which are called K and K prime. So we have a system which is a 2D material which has a Dirac dispersion, and the important thing about 2D materials is that by using electronic gates, you can tune the chemical potential, you can tune how much electrons you are putting in the material, and so you can tune the Fermi level in this material by a gate voltage. So what is twisted bilayer graphene? You just put these two things together and then twist it a little bit, and immediately you should be able to see that there is this bigger hexagonal patterns that you can see in that picture. If you rotate it, and you can go to momentum space, what will happen is that graphene's Brillouin zone is this big hexagon that I have drawn, okay? And because of this very large length scale Moire patterns, it will now be tiled by very small Moire Brillouin zones. So you basically take this big Brillouin zone and you tile it by the small Moire Brillouin zones corresponding to the larger length scale in your problem. Okay, so that's the story. And how large can it be? Typically, when people make it, the scale for the Moire in a graphene is about 30 times the graphene lattice spacing. Okay, and if I gave you just if I gave you essentially some argument about how much the energies would go down, you have a larger spacing, which means your momentum would go down. So your overall energy scales would go down. And what that would mean is you would go down by a factor of about 900, roughly speaking, okay, or about a factor of 1,000. Okay. So here is what happens actually when you, so this is a calculation. By the way, this calculation was done much before people could do it with, experimentalists could make these Moire patterns with a high accuracy. What you see is on the left-hand side, if I can get my, sorry. So on the left-hand side, you see a band structure, and what I want you to see out of that is that there is a blue band near zero, okay, and that's very large. You can see the scale, it's about 300 milli-electron volt or so on. On the right, just after that, is another plot at a different twist angle. These are different twist angles, and you can see that the band, there's a blue band which is almost flat. You can't see it on that scale, okay? For you to see, I have scaled it up on this side, and you see that the band width is now about 2 milli-electron volt, okay? Just for a comparison, graphene's bandwidth is about 3 electron volts. So suddenly you are doing condensed matter on an energy scale which is usually not available to you. You went down from an electron volt to 2 to 10 milli-electron volt as a bandwidth, okay? Now, when you have low bandwidth, one of the things that is going to happen is that it's a bandwidth is a measure of your kinetic energy. Your kinetic energy has gone down by this huge amount, right? So your system will be dominated by interactions because the ratio of interactions to kinetic energy has gone up, not because your interactions have gone up, but because your kinetic energy has gone down. And when people try to do this, they can vary the different densities. They see a bunch of different correlated phases. They see superconductivity. They see some magnetic phases. They see some insulating phases where there should be normally metals. And these are called correlated insulators. So, you know, there's a whole bunch of interaction-driven states that you see here. It's not completely understood. We are trying to understand all of these and so on and so forth. Okay, but today I would specifically like to talk to you about a little bit more about something called a bilayer graphene, which is just take these 2 layers of graphene, okay, put them together, not twist them, don't twist them, take them together. Take another of these 2 layers, don't twist them, but between the 2 and 3, just twist it a little bit. So you take 2 layers of bilayer graphene and twist it a little bit. Now, bilayer graphene, again, unlike graphene, doesn't have a Dirac dispersion. It has a quadratic band touching, and that's how it does have a band touching, but it has a quadratic band touching in this case. So what happens when you try to do this 2 bilayer graphenes together? There is a magic angle, which is about 1.1 to 1.3 degrees, where the bandwidth becomes a minimum. That's where you will have the most strongly interacting system. And these are some band structures that we had done, and others have also done, showing that, you know, as I go from 3 on the right to 1.3, the bands become very narrow. Now, when we were doing all this, our colleagues in TIFR, Mandar Deshmukh's group, they were actually doing the experiments on this system. And one of the things they showed is that unlike the twisted bilayer graphene, which has all sorts of correlated phase, the twisted double bilayer graphene is just a metal. It looks like a metal. We did some modeling with that. I'll not go into the details of the model. It turned out there was a simpler model people were using, which does not predict the metal, but if you look at it carefully enough and put all sorts of details in correctly, you do get the metal. And the main point that happens here is the following, that there are these 2 bands in the blue region, they overlap, okay? So when they overlap, what happens is that even at 0 doping, you actually get one set of electron pockets in the conduction band and one set of hole pockets in the valence band. So your net charge is 0, but you have both electrons and holes in your system. Okay. And what we did with Mandar here was that we showed that this, if you now apply a perpendicular electric field, this will remain a metal for some time and then it will get gapped out. And we did all sorts of detailed evaluations and showed that things match with the more detailed model where you keep all the parameters correctly. So here is your picture of what the low energy thing looks like. You see that at charge neutrality, the dashed line is the chemical potential. And so if I look at it, I will get this. You see the three red band, which is the, I believe, the whole band. And then you have these three pockets. These are the Fermi surfaces. And the blue is the conduction band. And then the conduction band has its own Fermi pocket. So you have pockets of electrons and pockets of holes present in the same material. And then, of course, you can ask, so now there is now a more strong evidence for this. This is called a compensated semi-metal. And now there's a very strong evidence which came later from our colleagues at Indian Institute of Science, Aninder Das and his group, where they looked at magnetotransport in this materials, and which kind of showed, I'm not going into the details of that, the system is really a compensated semi-metal, that you have these both electron and holes present in the system. Now you can ask, one of the things that you realize is that the densities are very small, the Fermi surfaces are small, okay? And you can ask, what is the effect of electron-electron interaction on these electron and hole pockets? But before that, you might ask me, oh, you said it's all a metal. Why bother? We know what metals look like. They're not much interacting. We know Landau's Fermi liquid theory, and it tells you that metals are essentially like Fermi gases with small changes in parameters and so on and so forth. To this, there was data then from Aninder's lab, which were told us that it's not a boring metal. So what am I plotting here? This is resistance as a function of doping in the system. And what you see is that the system is essentially metallic. However, if you go and look at very low temperatures, you see that there are these two peak structures in the resistance as a function of density, which cannot be explained by a simple non-interacting metal. The red curve, which is at 2 Kelvin, can be, but the lower curves cannot be explained. Why would you have a two-peak structure as a function of density? 5 plus 5, yeah. Okay, there was even more evidence from them. So what am I now doing is I'm taking this red cut going up along the, these are different temperatures, so I'm plotting resistance as a function of temperature. And when I'm doing this on these two red lines, you will see that the resistance behaves as T square, which is a classic behavior of Fermi liquid, a standard metal driven by electron-electron interaction. However, if you go close to this point where you had all these anomalies, okay, and you look for the resistance as a function of temperature, you see that at low temperature, it's almost linear up to about 10 Kelvin. But then at low temperature, you suddenly see that it gets a curvature, which tells you that it is T to the power alpha with alpha less than 1. Now, T to the power alpha with alpha less than 1 is very difficult to achieve in any metal. You can look at all possible mechanisms for resistance scattering, disorder, phonons, all sorts of things. Nothing would give you T to the power alpha with alpha less than 1. And this is a typical behavior of what is called a non-Fermi liquid. So basically, Landau's basic idea of metals being almost like the free Fermi gas has to break down for you to get a T to the power alpha with alpha less than 1. So what was our theory? The theory that we said is that, you have these electrons and hole pockets. They have opposite charges, and so they're likely to form excitons, okay? And if you have excitons, which are bound states of electrons and holes, and then you have a BC of these excitons, so it will be an excitonic metal, remember that these are Fermi pockets are shifted from each other in momentum space. So these would be indirect excitons, and then these can have a metallic state of excitons lying in this. Let me skip the details of the calculation. I mean, I'm happy to go through it if someone wants to know. What does it have to do with the resistance peaks? Turns out that when you form this exciton condensate, your local band structure modifies. Usually this one band, small band, now breaks up into 6 different bands. And if you do the calculation carefully, the left side is the experimental data, and the right side is a calculation that we have for different values of screened Coulomb interaction. And you can again see this 2-peak structure arising because of the exciton condensation. Okay? Then just to point out that if we had a non-interacting answer, that would be the flat line in the middle, which would show that there is nothing really happening in the system. Finally, what about the idea that you had a t to the power 2/3? If you are in a critical phase where you are just about to condense to an exciton, okay, you will have critical fluctuations. The exciton order parameter is a bosonic order parameter because you have combined electrons and holes together. And you can look at the fluctuations of this order parameter. And at the critical fluctuation, what happens is that you see that there's a damping rate which goes as omega over q, basically. Okay? And this can be shown analytically, this can be shown within our calculation, etc., etc. Now, what happens when you have such a critical damping of omega over q is that you can just do dimensional analysis and say that omega must scale as QQ. Yeah? You will have a omega square and omega over q, so you basically equate them together because they have to dimensionally be the same. So omega must scale as q cube. If you take that kind of a relation, you will get a density of states in 2D where g of omega goes as omega to the power minus 1/3. And then what does this g of omega sit? Because now you want to calculate a scattering rate by some Fermi-Golden rule. Your g of omega will come in. The Bose distribution will make an appearance because now you are scattering of these fluctuations of the exciton, which are bosons themselves. Okay? And then if you do a scaling and can go to a variable which is omega over t, you will pull out a t to the power 2/3. Okay? It also leads to the fact that the electron lifetime is omega to the power 2/3, which is a typical characteristic of a non-Fermi liquid. Okay? So let's not go into the details of when it breaks down and so on. So we do get a sense of both of these, the 2 resistance peaks and the t to the power 2/3 behavior of the resistance within this theory, which says that you had electron and hole pockets. They formed an excitonic condensate. The condensate itself at low temperature led to these 2 peaks. At higher temperatures, you had fluctuations of this condensate, and that led to the resistivity going as t to the power 2/3. So before I conclude, these are the collaborators. Unmesh Ghorai is a graduate student who has just graduated from TIFR. Priyanka Mohan is an ex-postdoc who has worked on this problem. And then experimental collaborators Mandar Deshmukh and his group in TIFR, and Anindo Das and his group in IISc have provided we have had strong collaborations with them. So maybe these are the conclusions. So Moire materials offer a unique platform to study strongly correlated electrons. You have a new knob to tune the kinetic energy, which means you have a new knob to tune the effective interaction strength, interaction by kinetic energy. There are magic angles where the bandwidth is minimum and interaction effects are clear in twisted bilayer graphene. And twisted double bilayer graphene at the first look does not look like very strongly, it looks like a metal. But if you look at it carefully, you will see that there are these low temperature peaks in resistance, and there are t to the power 2/3 non-Fermi liquid behavior. which we believe is coming from the fact that you are creating an excitonic metal and its fluctuations are driving your resistance. So I'll stop here and maybe take questions.
Thank you. Okay. Are there questions?
Yes.
So the band structure, did you get?
No, so what tight binding is hard to do here because the unit cell is so large. So and there's very little DFT here because you're
Sure.
really talking about very large unit cells, and also very small energy. DFT would not have accuracy on that scale, right? So one of the things the people do is what is called the Bistritzer-McDonald type model. So well, maybe I'll just give you a. I had a picture somewhere. So what you do is that you say that okay, you have this Dirac points near the two ends, the circles, right, that I have drawn on that big hexagon, and you are tiling with them, and because of your Moire potential, you are scattering to this. Now, because you are at some odd incommensurate angle, if you start tiling this, you will not be able to match at the end because some incommensurate thing is not exactly matchable. So what Bistritzer and McDonald showed, roughly like a K dot P perturbation theory stuff, is that if the angle is small, then you go up to whatever 10, 20 such Brillouin zones.
Sure.
Low energy physics band structure is essentially doesn't change, and you can go a little higher.
So it's K dot P.
Yeah, so it's essentially a K dot P.
And so how did you draw conclusions about, you said strong correlations?
Yeah, so the strong correlations, so in twisted bilayer, it's much clearer because, for example, if you look at 2, there's an insulator, okay? So filling up the band is like going to 4, okay? So at the middle of the band, you are suddenly having an insulator. Okay, that would not have come from a band structure calculation, would not have given you that. Okay, so and then there are of course superconductivity and other things. But the cleanest thing is that at 2, you suddenly see an insulator, a reasonably good insulator. In twisted bilayer, it's less clear, and at first sight, as I said, it looks like a metal unless you look very carefully. And this was my evidence for the fact that I think the main evidence is that you see this curvature like this, the resistance going like that, rather than going like that, which is, if you really put numbers there, it will be about 0.67. But both you and I know that 0.67 can be 0.7, 0.73. But that's a fitting issue. But what is definitely clear, it's less than 1. That's very hard to see without any sort of interaction effects. Thank you.
So we move on to the next talk. It's Out of Time Order Correlators and Chaos in Quantum Billiards by Tibra Ali.
I can see some of my students are here, and it's been a very long day. So we are all very tired, and I will give a gift. My talk will be very short. And I can assure you this will be the simplest talk given at this conference, because it'll be a talk about the quantum mechanics of one particle inside a billiard. So please, I know that we are supposed to have questions at the end, but maybe if there are some questions from the undergraduate, you can just like holler or raise your hand, and I can interrupt and break the tradition. All right, so the topic of my talk is out of time order correlators and chaos in quantum chaos. So obviously I was not awake when I wrote that. In quantum billiards, that should be, okay. So this is work that just appeared a few months ago, actually during the revolution, and this is the archive number. And it's a work that is done with two of my undergraduate students. So at Brack University, we have a tradition. Well, students have to do an undergraduate thesis, and they did this thesis. So I'm really only reporting. 95% of the work was done by them. I'm just here to promote their work. So here are the two students, extremely bright young men. As Ador and Naim. Naim couldn't come here because Ador is now a research assistant at Brack University, and Naim is a TA, and apparently he is just teaching so many lab classes that he couldn't make it. So, but these are the real hero of this talk. It's also, for me, it's a very, very meaningful and emotional moment, because I was a student of this university, and the person who taught me quantum mechanics, who gave me introduction to quantum mechanics, was Professor Lalit Mohan Nath. And I remember him fondly, and he had a huge impact on me, not just in terms of physics, but in terms of my worldview, in terms of my politics, in terms of my understanding of what it means to be Bangladeshi. So I feel extremely honored to be speaking in the Lalit Mohan Nath Memorial section of this talk. So this is the outline of the talk. We are going to say a little bit about what is chaos, and I'm going to just give you a very brief discussion of what a classical chaos is and also quantum chaos. And then, I will say why OTOC. Why are they good for studying quantum chaos? And I will not give you a very overarching explanation, but I will give you a very model specific, specific to the very simple system that we're looking at. And then we'll talk about, I'll introduce you to the billiards that we will be playing with. And then I'll discuss the semi-classical approximation that was derived by a French group that was crucial to our calculation. And then, how the billiards that we looked at, and then, their so-called quantum Lyapunov exponent, their Ehrenfest time, and all that. So it'll be a very simple application of quantum mechanics, but I had a lot of fun doing it. All right, and then some conclusion. And on the left, we have the picture of a very typical classical chaotic system known as the Lorentz attractor, which you may have heard of. All right, so what are the characteristics of classical chaos? Well, that's a huge subject, but in short, what we mean is that when we say there's a chaotic system, is that at least, the system is extremely sensitive to initial conditions, right? So if delta x is basically the variation of the initial condition, And for a chaotic system, the growth of this the coordinate of two initial conditions will grow exponentially with time. Here, lambda is a positive constant called the Lyapunov exponent, and it is one of the numbers that characterize a chaotic system. And here's a cartoon picture where we have, I'm going to break tradition and use that one. So that's the little deviation, the initial deviation of the initial condition of two particles, that's a delta x0, and with time they're exponentially sort of diverging from each other. And this exponential divergence doesn't only have to be in physical space, but it can also happen in phase space. And here is a realization of this. This is a very simple two-dimensional billiard known as the Sinai billiard. It's named after someone, not after the mountain. And it's a model of some sort of some conduction gas. And here you have a square and you scoop out a circle from them. And here we have an initial condition, 2 points which start so close to each other you can't even see. And then after a few bounces, you can see that they are diverging. So if this circular thing was not there, of course, these two things, you would not ever see them diverge. So it's really the presence of the circular wall that gives rise to this divergence behavior. So that's really what makes the system chaotic. So there are other features of classical chaos. So for example, you can have a system where you have some tunable parameter, and the system can, for example, switch to a chaotic behavior. So here we have a Poincare section of a phase space. A Poincare section is just, you have some classical mechanical system and you take you basically take some cross sections and then you impose them on each other, something like that. And that's basically what's called a Poincare section. And here you see that there are all these beautiful regular patterns, and that means that, the motion is integrable. But at some point, it can switch to an irregular pattern, and then, the trajectories can fill up the phase space in a way such that you get, it kind of fills up the whole of phase space. It's a phenomena which is sometimes called ergodicity. So as an example, I give you here what is known as the Cos billiard. And here, a Cos billiard is defined by this equation, which is a parametric equation. And for epsilon non-zero, it has this kind of, orange-like shape. So it's not exactly a circle. And so I'm just showing you how some trajectory tends to fill up the whole of the billiard. So this is basically what I'm saying gives rise to this, in Bengali I would say hijibiji or busy pattern, right? So what about quantum chaos? Well, quantum mechanics, apparently, it's hard to define the idea of chaos in quantum mechanics. And one of the main reasons is that there is no such thing as a phase space in quantum mechanics. You can define something analogous to a phase space, but there is no positive definite probability distribution on such a space. And then, so, what do you mean by two particles who are close to each other? Well, you might say, okay, why don't I take, say, the inner product between two states, quantum states? That could be a measure of their distance. But if the system is evolving under unitary transformation, we see that the unitary transformation will preserve their inner product, right? So we see that with time evolution, their distance is not going to increase. So there are lots of ways of characterizing quantum chaos. Here I will just touch upon one. And one of the things is that people have observed that if you have a classical chaotic system and then you quantize it, and then you have their eigenvalues, the energy eigenvalues satisfy some kind of a distribution, and this is called, it's a conjecture called BGS conjecture, and the conjecture is that if you take the differences of the eigenvalues of the Hamiltonian, and you see that they turn out to be random, and if you plot them as a function of the difference of the energies, they give you some random distribution which follow some Gaussian orthogonal distribution or Gaussian orthogonal ensemble or some other higher order or Poisson, and there could even be Gaussian unitary. It's orthogonal ensemble. So this is basically what people say. There are other features of quantum chaos, but this is basically what people say about characterized quantum chaos. Now, quantum chaos is extremely important physically, and recently, in the analysis of black holes in ADS-CFT, quantum chaos is an idea that has been explored a lot. But also in everyday life, for example, the whole problem of thermalizations and stuff like that, quantum chaos, and also how, the classical world emerges, right? So anyway, I'm just kind of trying to motivate you that quantum chaos is an interesting problem to describe. So why OTOC? So, we have this nice way of describing chaos. Why do we need this thing called OTOC, and what is an OTOC? So OTOC is an out-of-time order correlator, and they were studied in 1969, and to study the semi-classical behavior of superconductor by these two Russian physicists, Larkin and Ovchinnikov. And I could not find exactly the citation timeline of this paper, but I found a citation timeline of one of their other papers from that era, and they basically have zero citation until like the 21st century. So it's kind of happens physics. So if you write a beautiful paper and you're happy with the paper and it gets ignored over 20 years, that's fine, physics papers, even good papers get ignored for a long time. At least that's what I tell myself. There are other examples like Montanen and Olive and people like that. Anyway, so this is the definition of a out-of-time order correlator. So as you can see, there are four operators in the expectation value, but one of them is at time 0, the other one, B, is at time t. And these are Heisenberg operators. As you know, in quantum mechanics, you can have the time dependence of a system either in the state or in the operators. So here they're Heisenberg operators. So these are out-of-time order correlators. And this is related to something called Loschmidt echo, but I won't go into that right now. So why time order correlators? Because if you've done a little bit of quantum mechanics, and so Dirac gave us a prescription about how to go from classical mechanics to quantum mechanics, right? So you can turn that back and you can say, okay, I have a quantum mechanical system and I want to go to its classical mechanic analog. Well, then basically you would take the h bar, go to zero limit, that's your classical or quasi-classical limit, and you would divide the commutator by IH bar, and you would pretend that is somehow, at least numerically, it's kind of giving you your Poincare bracket, right? If you put the Poincare bracket in, if you put the commutator in some expectation value. So if you do the same thing with the lower commutator, you see x is at time t, and px is at time 0. Then this basically, if you compute the Poisson bracket, the Poisson bracket gives you exactly what you want to compute to compute the Lyapunov exponent, right? So that's where the motivation comes in, why we should be looking at OTOC to understand quantum chaos. So this is, again, so for us, we are going to take Hermitian operators. So if you take Hermitian operators, the definition of the OTC, becomes, just the commutator of BTA minus sign, expectation value. The T subscript should be the time dependence. Sorry for that. So motivation, as I said, for this comes from ADS-CFT and black holes, and that's a very long story that I won't be able to go to. And also, but Kitaev, in one of his recent talks, gave a motivation where he said that there should exist if black holes are supposed to be kind of some very extremely chaotic system. So Kitaev and others were discussing their holographic analog. So the idea is that if in such a system there exists a quasi-classical or semi-classical limit, then according to the argument that I gave in the previous slide, the OTOC, which is kind of the square of the Poisson bracket, should have this form in that semi-classical or quasi-classical limit, right? And this lambda, which comes from the OTOC, this is what Kitaev has called the quantum Lyapunov exponent, because Lyapunov exponent before Kitaev proposed this was not something that, as far as I know, was something that was relevant in quantum chaos. And so basically we are saying that as long as Ehrenfest theorem is valid, we should have some sort of regime there. There could be a quantum mechanical system where there is no such semi-classical regime, and there, we would have to use some other way of describing its chaotic behavior. So, so this is what we are going to do. We're going to take the Hamiltonian for a two-dimensional billiard. So this, if it's a square billiard or a rectangular billiard, then we don't expect chaotic behavior in the classical regime. But if it's a billiard which has this kind of irregular shape, here it's really the dispersing walls, these walls which are kind of curving, they're the ones who create the chaotic behavior. And so, sorry, what was there a question? Oh, your mic is on.
Sir, I have a question.
Yes, please.
So you said black holes are chaotic, but how do we know that? Like, we don't see inside the black holes, or it's just a singularity inside, right? So how do we know that black holes are chaotic or not?
These are ADS black holes, and so yeah, there's a long history of these. We should really talk about that outside. I can give you references, and or maybe you can answer that question, but there are good arguments why black holes should. There are some arguments why black holes are the fastest scramblers of information in the universe. So, of course, it's not experimental, but yeah, that's a very good question. Okay, so this is basically the potential is basically a particle in a box. It's a two-dimensional box. And here, this is called the diamond billiard, but I work with two undergraduate students, and And I told them that I would like to call it the Superman billiard because it looks like the logo of Superman. And when they wrote the paper, they put the name in. So maybe that's the reason why it'll get rejected if it does. So, so to compute here is like one technical slide. To compute the OTOC, we are going to take, you don't have to take the average to be a thermal average, but that's what we are going to do. Thank you. So I got 5 + 5 minutes. So this is basically a thermal average. And those of you who took my recent class on statistical mechanics, this is essentially, I'm going to call this the macrocanonical ensemble because it depends on temperature. Here is the exponential dependence. And this is, Cn is the microcanonical ensemble because that the n, which is the energy level, it's fixed in small cn. So Ct is the macrocanonical example. The big T is the temperature, small t is the time. Here n is the energy, and small t is the time. So this was initiated by the study of quantum chaos of quantum billiard using OTOC was initiated by Hashimoto et al. And so here's the classical billiard right below. And so what they did, they plotted the OTOC and they compared it with the OTOC of the circle billiards. The circular billiard is not chaotic, and they couldn't really find a region where there was an exponential growth. So they looked for it, but they couldn't find it. But of course, this paper started people asking the question whether, you could find a semi-classical region and a quantum Lyapunov exponent in a simple billiard. So this was found by Jalabert et al. And it turns out that to find the semi-classical expression for the OTOC, you have to do a very careful analysis of the paths in a path integral configuration because there will be correlated paths. So those correlated paths would interfere constructively and they would actually, so it's actually a non-trivial problem to find the semi-classical, regime. And that was solved by Jalabert et al. Very nice people. They gave, we couldn't figure out a factor in our calculation, so we emailed them and they sent us like 25 pages of their calculations. Amazing people. So this is the formula that in the semi-classical regime, and from which, this is for the low temperature, you get something like this, where lambda g is a geometric Lyapunov exponent. And so the crude or the Lyapunov exponent is square root of 3 lambda g v tilde, where v tilde is the RMS velocity at that temperature. And then, they found that, so these are the different OTOCs at low temperatures, and then here is the region where you could find the exponential growth. Here we have a logarithmic scale, and that's why it looks linear, and they could figure out the Lyapunov exponent as a slope. And this is just a technical thing I'm going to skip. And that's so our billiard, we looked at 3 billiards, the Sinai billiard, the cardioid billiard. The cardioid billiard is the Cos billiard, but for the parameter equals to 1, and the diamond billiard or the Superman billiard. And we had to compute the classical Lyapunov exponent. Here's the data, nothing very exciting. And then we plotted, numerically plotted everything using Mathematica. It took long time, sometimes 4 or 5 hours, to plot these graphs, but these guys did it. And one thing that we saw was an anomaly in the Sinai billiard is that at the very low temperature, there is no exponential increase in the Superman and the cardioid, but in the Sinai, there was. So we looked at the low energy microcanonical ensemble, and we saw that the Sinai billiard had an exception, an anomaly, that it was sensitive to the low energy. The low energy was also kind of getting some exponential increase or a really sharp increase. So one of my students, he had the idea that let's look at the wave function of the low energy. And here the wave function, and we see that for the Sinai billiard, it kind of knows the geometry. Because of the symmetry, there are 4 maxima or minima. So the ground state wave function kind of knows the geometry of the billiard. Whereas here, it just blah, one bump. So somehow the geometry of the Sinai billiard is telling us that, yes, this is a chaotic system, we know. So that's basically what's exciting. So, and here is the calculation, which is we are comparing the classical and the quantum, and they're pretty good. The diamond is not so good, but it is what it is. So we are happy. These are the geometric. So Lyapunov exponent has a dimension of inverse of time. Here we are multiplying by some thermal factors to make them pure numbers. And here's the long time behavior of the OTOCs. The really wild fluctuations of the low temperature ones, as you go up in temperature, there are more and more modes contributing, so they become more and more smooth. So and so this is the part where you have an exponential, and then this is where the wave function kind of spreads out. So the time before that is what we call the Ehrenfest time. And I had a little conjecture that the Ehrenfest time should be proportional to 1 over square root of t, and here's the fitting of the data. And this was based on some very basic quantum mechanics that I learned from Professor Lalit Mohan Nath. So I was very, very happy that I was able to use my old quantum mechanics knowledge for that. So these are the conclusions. The OTOCs give us a new and intuitive way of examining the chaos that is in some sense much closer to the intuition from classical chaos. The quantum Lyapunov exponent we found is close to classical Lyapunov exponent, and that is just saying that, well, Ehrenfest theorem holds until Ehrenfest time. We found a bit of a surprise in the low energy of the Sinai billiard. And then we found an intuitive way to estimate Ehrenfest time. And we found new features in the long time OTOC. So that's it. Thank you.
Yeah, go ahead, please.
Yes, beautiful talk. Thank you. Of all the billiards out there, why were you interested in the Superman billiard?
Because my students I said, just go and look for some interesting billiards for you to do your thesis. So they just chose, the Bumwich Stadium billiard is something that everyone does, right? Mm-hmm. That's the most, but that has been done by this French group and also Hashimoto. So they reproduce Hashimoto's result. So then we wanted, and they understood this new paper. So we wanted to see if we could apply those results to a few other billiards. So it was really random. So yeah.
Fair enough. Yeah. If I could ask one more question.
Please.
So the cusp on the cardioid, did that cause any sorts of problems with either the semi-classical limit because of diffraction effects or discontinuities in your surface of section?
I think my students did the numerical analysis. I don't think we have to throw away any point for that. Maybe the resolution was enough. I know that when we were simulating the diamond billiard, because the way that Mathematica works, because we had to define a piecewise function. Mm-hmm. Sometimes because of the accuracy, some of the trajectories would escape. Mm-hmm. So we would have to look out for that. I didn't hear any complaint about the cusps. So I'm assuming no, but but maybe we should go back and look. Maybe there's some interesting physics that I'm very new to this field. I don't know about that could come from there. So yeah, some sort of, what do you call those things? The wavelets that you get from cusps, right? Or yeah. So yeah, sorry. Yeah, I don't think so.
Okay, thank you.
Bro, what is your low? How much is the low energy? What do you mean by the low energy? Here,
Sorry?
low energy.
Low energy.
Yeah.
Its temperature is like 5-6 degrees. So on the right, you see the log of the temperature, the log 2 of the temperature. So it's there on the logarithmic scale.
Yeah, and then what is Ehrenfest time?
Ehrenfest time is the time as you can see, so we have like semi-classical behavior at the beginning. At the beginning of the billiard, and then I didn't put those slides. I should have, sorry. I don't know where they are. But yeah, we also have slides like these. And then basically this is the region where we do have, so over here, we actually have data for the region where, you zoom into this place where there's an exponential increase. And after that, it kind of, it becomes saturated. So basically what happens at this point is that the wave functions, the intuitive understanding is the wave function, say, of a Gaussian spreads out over the whole billiard. So that's when we expect the Newtonian approximation to break down, the Ehrenfest theorem to break down. So Ehrenfest time is the time up until which we can use the Ehrenfest theorem.
Oh, thank you.
Yes, please.
Hello?
Yes.
Yeah, a strange question come to my mind. Yeah, it may be weird. In classical chaos, say Lyapunov exponent is a measure of characterization of chaos. But another issue is the frequency distribution. It shows the broad distributions. So do you have some analog kind of thing in quantum chaos? I don't know.
I don't know about frequency distribution, but I would think it would be close to what this is. Here the distribution of the level fluctuation, the energy level fluctuations. Probably that's something like that. So yeah, that would be my guess. Yeah.
Thank you.
The other questions?
So when you did the calculation for the microcanonical averaging, you wrote an expression for small CNT where the commutator of xt and p are being sandwiched between energy eigenstates.
Yes, this one.
Yeah. Could you replace the energy eigenstates with any other state, meaning other operator eigenstates?
Yeah, but calculationally that would probably be, we are really looking at free particle in a box, right?
Yeah.
So, so the energy eigenstate is the best thing to use. Another thing you have to keep in mind in doing this calculation is that Ehrenfest theorem has in it the derivative of the potential. If you remember your quantum mechanics, the expectation value of the derivative of the potential. So when you have a wall, which is an infinite wall, which we do, that derivative doesn't exist. So there are subtle questions of domain and range of operators you have to take into account. So in taking this, in taking these states, which states you want to compute this, you have to keep that in mind. And there are papers which tell you that, so this is something that is the right thing to take. So if you take any other operator, arbitrary operator, you will get numerical inaccuracies because range and because the mismatch between operator and its domain.
Thank you.
Any other question? Go ahead.
In many of these stadiums, there are concepts of classical scars, certain trajectories which are not chaotic, but they lie in the sea of chaotic trajectories. Have you thought about looking for similar quantum scars in this?
Oh, there are quantum scars.
No, I know there are, but I'm just saying.
I don't know how to transform them into an OTOC calculation. So, OTOCs, they're a new way of, they're a new tool in the toolbox of the quantum chaos physics. So we just wanted to see, whether we could apply those.
So these are part of some essentially almost integrable like states. So OTOC should have a different behavior there.
Well, maybe that's something we can look at, but thanks for the idea,
If there are no other questions, let's thank the speaker once more. Okay, so that's the end of this session.